Thank you for the introduction. So this is joint work with Jaime Arias, Kyungmin Bei, who is here, Carlos Solarte, Peter Olewski, and Frederick Röhm. So the motivation in this work is that we are considering some models that are parametric timed automata that I will explain just in a couple of slides. And they extend automata with timing parameters. For these, we have timed model checking procedures that are available, and also some parameter synthesis that are implemented in the tool which is called Imitator. And these synthesis algorithms, they would tell you, here are the parameters values for which some property is, some type property is satisfied. These are implemented through dedicated algorithms, meaning that every time we have something new or a new heuristics and so on, there is a huge work of implementation, which is not, well, it's working, but it's not that good. And at the same time, we also consider rewriting logics and modes, which are an expressive formalism and language that can deal with concrete executions of real-time systems. But to handle symbolic execution, what can be combined with SMT solving and then handle symbolic executions, which will be important in the case of parametric timed automata. So we have two approaches. It's a bit in line with a previous talk, where we have several models, several tools, and we want to get the benefit from both worlds and put things together and see how one approach can help us with the other. So I will first explain some background about parametric timed automata and rewrite theories and modes. That will be quite quick, but it will allow you to know what we are talking about, what are the objects we are interested in. And then I will show you how we designed a rewriting logic for parametric timed automata. So rewrite theories, how we could carry on symbolic reachability analysis, parameter synthesis, and also use the strategy language that is provided by Maude to have better algorithms for handling parametric timed automata. And then I conclude and give some hints for future work. So let's start with a timed automaton. So this is a small example where you have a coffee machine that can be idle. You can press a button and start, and you can add sugar maybe several times by this transition, and then go to prepare coffee, and after a while, coffee is done and you become idle again. So a timed automaton is a finite state automaton with sets of locations. There are these idle, add sugar, done, and preparing coffee, and actions in between. So for example, B start, B sugar, button sugar, cup, and so on. And you also have in a timed automaton a set of clocks. So here it's X, and you have two clocks in this automaton, which are X1 and X2. These clocks are real valued variables that evolve all at the same rate. And they can be compared to integer constants in invariance in guards. So for example, if we look at here, so here we have a guard to take this transition that says that clock X1 should be equal to 10. And we have invariance saying how long we can stay in, what are the conditions to stay in a location. So for example, here, X1 should be less than 10 or equal to 10 to stay in done. Clocks can be reset, and this is expressed here on transitions. So here, if you press button B start, you not only move from idle to add sugar, but you also reset the two clocks, X1 and X2, right? In parametric timed automata, you have also a set of parameters, P, that are representing unknown constants. So for example, here in this location, add sugar, you have associated with it an invariant which says x2 should be less than or equal to p2. So p2 is a parameter, meaning, well, it's a constant value, but we don't know the exact value of that constant, right? So this is the models we are interested in, where we have the usual problems of reachability and finding these things, plus parameter synthesis, which is basically a problem of saying, well, so which values of my parameters is my property satisfying? Well, so how to analyze this? So when we do model checking on parametric timed automata, we use the parametric zone graph, where we have states that are symbolic and they are a pair with a location and a parametric zone that is a constraint. So let's take again this example. Initially, you're in state idle, and you know that the two clocks, well, let's say they are equal to 0 at the beginning. So the two clocks are equal. You have a constraint x1 equals x2, and we assume that everything is positive in the initial state. So, well, parameters are positive and clocks are positive or not. So this is a symbolic state representing the initial state. In the behavior in parametric timed automaton, when you're in a location, time can elapse. And so here you know that at the beginning, x1 equals x2, and maybe they are 0 at the very start, but then time can elapse. So in the symbolic state, you will express this feature. So what you know is that x1 equals x2. They have some value, but depending on the time that passed, well, this value can be different. And then we construct the parametric zone graph by taking possible transitions. So let's start with the first one. So from idle, you can take B start. There is no condition to check on B start, and you reset both clocks. You go to add sugar. So we have to be careful, because when we end up in a location, the invariant of that location should be satisfied. So here we have x2 smaller than or equal to p2. It should be satisfied when we arrive in add sugar. But since we reset the two clocks, that's fine here. Right. So we arrive at the new symbolic state saying we are in add sugar. The two clocks are still equal. And we know also that x2 must be smaller than p2. Yep. Okay. And then we can continue. So from there, we can either press a button to get a new sugar, and we get this symbolic state, which is a bit more complicated, or we can get a cup when x2 reaches p2, and we get this new symbolic state. And we can continue, go on and on again. The problem with parametric zone graph is that it's possibly infinite, and so there are dedicated model checking semi-algorithms that would check your property or find your parameters. So they do the exploration, and once they arrive at some state where the property is satisfied, they will collect the information. And maybe it's enough if you want a witness of what's happening, or if you want to synthesize all parameters, maybe you will go and look in other branches. So these semi-algorithms, they can provide you, well, they are not guaranteed to terminate, but when they do terminate, they give you the exact value. And if they don't terminate, they can provide you with under or over approximations of the result. Okay. If we said that we would express that in rewriting logic, so we have a quick look at what a rewrite theory is. So we have in rewrite theory, we have an equational theory with an order sorted signature and a set of possibly conditional equations, a set of labels, and conditional rewrite rules that say basically I can transform from a term into another term if some condition is satisfied. So rewrites are such that you take a term t, you rewrite it in t prime by applying a rule to a subterm of t and getting then t prime with this rule. With the rewrite theories, there's a tool and language that is associated, which is called Maude, and that allows for specification and analysis of these rewrite theories. And a short look in the syntax is here, so it can allow you to declare a rewrite theory, declare the sorts that are used there, if there's some subsorts relations between some of them, declare some logical variables of some sort, operators, so an operator from S1, Sn to S, conditional equations, so t equals t prime if some condition is satisfied, and conditional rewrite rules that express how the rewrite is done under some condition. And there are also analysis capabilities that are provided by Maude, which are, for example, rewriting a term or doing some symbolic rewrites using the SMT search command. And there's a strategy language for user-defined analysis strategies, and we'll have a quick look at how we use that. So now we have parametric timed automata, and we want to use the power of rewrite theories to get some better analysis or different or more analysis for parametric timed automata. So how do we transform parametric timed automaton into a rewrite theory? So first of all, so this is the example of our coffee machine. First of all, we say we'll use real, and that will be used by the SMT search. We have several sorts. There are state, end state, D state, and locations. So locations will be the states in the automaton, and we have two kinds of states, non-delayed states and delayed states that are that refine state. And that will allow for expressing the fact that you can, in a location, let time pass, and then you can, from some point in the location, take a transition. So that will allow for differentiating these two cases in the runs. Then you have the clocks that can be declared, the parameters that are declared, and the time elapsed, which is declared as variable t here. And then there are some constructors for locations and states, which are operations that are basically the name of the location and say it's a location. And the operators, you can see there are two types of them. One is concerning the delayed states, and the other one is considering the non-delayed states. So they have a similar structure, and the type of brackets in the first part is a bit different. So you will have the location and the values of the clocks in both cases, and the values of parameters, the parameters in the second part. So then let's see how we model something that is appearing between add sugar and preparing coffee. So there are two things. One is letting time pass, and the other one is taking the transition. So basically, if I'm in location add sugar, I can do either, I can have a rule that is, I have a tick, and I'll take some state where I'm in add sugar with two clocks, x1 and x2, and some parameters p1, p2, p3, and I'll get a new state where I'm still in add sugar, and I have, well, time has passed, so I will increase both clocks, x1 and the x2, by the same time, that is t here. And this can happen only if the invariant of add sugar is still satisfied. So this x2 plus t, so the one that I get in the end, is smaller than my parameter p2, and t is positive time or null time. Okay. The other rule is expressing how I get from add sugar to preparing coffee, and it's similar. So you start from the other type of state, and you're going to preparing coffee with two clocks that haven't changed because you are just taking the transition and not letting time pass. And you can do that only if what you get in the end is satisfied. So x2 is smaller than p3, and the guard on the transition is satisfied. So x2 is equal to p2. Okay. So the translation is quite easy. Well, standard reachability with these kinds of models adds a new variable with each tick. So if you do standard reachability, you get a blow up and non-termination when desired states are not reachable. So you can use some approaches like folding that ignores new symbolic states that are subsumed by another one, and then, well, you get benefit from it. We proved in the paper the correctness of transformations from parametric timed automaton to rewrite theory, so what I sketched just before, but also that symbolic executions that I'm going to detail a bit afterwards correspond to transitions in the parametric zone graph, and that symbolic reachability with folding terminates when the parametric zone graph is finite, which is good. So how do we do symbolic reachability analysis? We use the SMT search capability of the language, and we say, well, here is an example. So we want to start from the state idle with some values x1, x2 for clocks and parameters p1 to p3, and our goal is to find whether there is a path to a state where we are in done with other values for the clocks and still the same values for parameters as they represent constants. And we want to check whether it's possible to reach done such that the two clocks have the same value, and x1, well, the one you started with is positive, and p1, p2, p3 are positive. So a solution is expressed like this. So you get a solution with these representations which are introduced by the search. So this dash 3t, dash 1t, dash 2t, etc. And it says, well, you can get to that state where two clocks x1 and x2 that you initially had were equal. Everything that you stated was positive is positive, and, well, some more constraints. And in the end, something we are interested in, this dash 3t is less than 10, which means that the target clock, so this x prime 1, which is here, is less than 10, and also that dash 1t plus dash 2t is equal to p3, so it tells you that x prime 2 is which is here, so the same thing plus dash 3t is greater than p3. Okay, so that gives you some relation between the clocks and the parameters. Fresh variables that are applied when introduced when applying tick rules may lead to an infinite search. So we use folding and subsumption to stop the exploration of states that are subsumed by one that has already been encountered. And we designed a new reachability command to implement that. So I won't detail that. Now, in parametric timed automata, another thing we are interested in is EF synthesis. So the EF synthesis problem consists in computing the set of parameters that allow for a given property to be satisfied. For example, we have this formula, EF x1 different from x2 and preparing coffee, that states, is the location preparing coffee reachable with different values for the two clocks? And so can I reach it? And well, let's see how we compute that. We can do a SMT search, starting from the initial state, so always the same thing, getting to some location with new variables. And we want this location to be preparing coffee. We want the two clocks that we obtain to be different, that is part of our property, and the parameters have positive values. And the result we obtain is that P1 should be smaller than P2, that should be smaller than P3. So you see it gives you constraints on the parameters for this property to be satisfied. We also use the strategy language of Maude to express reachability and synthesis based on a strategy. For example, you can analyze the system assuming at least one dose of sugar is required. So in general, when you're model checking parametric timed automata, how would you do that? You would modify the automaton, but that is error prone, and that is not very satisfactory. So here, the approach is to define a strategy that will say, well, what happens with sugar? So I can stop when I reach done, or if I'm in location, add sugar. If I need to add one more sugar, I do it. And otherwise, I apply any rule. And yeah. So that allows to focus on dedicated properties and strategies. So some highlights of this work are the following. First, we provided symbolic analysis methods for real-time rewrite theory. We provided some analysis methods for parametric timed automata. And there is something I said at the beginning, that we have a tool, Imitator, that is dedicated to parametric timed automata with heuristics and algorithms that are dedicated. But for example, this you can't express. It doesn't allow for comparing clocks in the property, which is something that is possible here and easily possible. We have done folding-based symbolic reachability analysis. And so these new analyses for parametric timed automata that allow clocks and parameters in state propositions. We have introduced user-defined analysis strategy that can allow for easy prototyping of heuristics and for applying that to some benchmarks. So the perspectives of this works are defining a timed strategy language, consider larger classes of real-time rewrite theories, and extend Maude LCL-CTL model checkers to a symbolic setting. And something that is interesting here in this easy prototyping is, as I said, we have heuristics in this Imitator tool that take time to implement, and the use of strategies provided by Maude could be helpful in designing these heuristics and checking them before implementing a dedicated tool with, well, appropriate data structures. Thank you for your attention.
Thank you. Questions? Yes, please.
Thank you for the talk. I just want to clarify what's the range of this, what kind of programming can you handle? Do you cover concurrency and shared variables? Maybe.
Well, so we are, well, the input model is a timed automaton, so it's not a program.
It's not a program. That's true.
And of course, well, when we have timed automata, we model systems where there is concurrency, there is non-determinism, and all these kinds of features.
This also can cover those features, right?
Yeah.
Concurrency.
Yeah.
But for example, if you have two threads, each of them have a parameter as a time passing, and then you just compare the constraints with these two parameters, and you see whether they have deterministic comparison or something like this.
Well, what I didn't show is that these parametric timed automata, there are a set of automata that can be synchronized, and so they share the clocks in these models. But then the clocks you can manipulate on each automaton. So you can reset them or not reset them. So they just evolve at the same rate, and yeah, you can compare them.
I hope I can ask another question. So, because I'm also working on some automata, also
Yeah.
symbolic execution. So, I often been asked how do you compare this technique, this very explicit clock manipulation, with another kind of time verification, which is implicit clock, which are just invent the clocks as variables, and you have explicit forwarding of the clock. Like you say this step will f clock by 2.
Yeah.
So you're aware of this, difference of this?
Yeah, that is something that is not allowed in the. Well, you can. Well, if you say I advance, that depends on what you allow. If I understand well what you said, you say, well, I have this clock x, and I want it in the next step to be x plus 2. Right?
Yes, it's a variable. It's a variable. It's not a time variable. It's just a variable.
It's not a time variable.
It's not a.
Okay, so yes, we can allow for variables, for discrete variables.
Thank you so much.
Yeah.
Yeah, so you are like translating the PTAs into like the rewriting mode, right?
Yeah.
And then one thing you said, which was intriguing me, is you can easier modify the rewriting system, right?
Yeah.
So now what I was thinking is, can you then translate it back into the time automata, or is that not possible?
Well, that depends on what change you do.
Yeah. So in general, it is more powerful, or
Yeah, this is, well, you can express a lot of things in the rewriting
yeah,
field.
which is what I'm thinking. So is it the case that when you translate like PTAs, you get fragments which is basically easier?
You mean what's easier?
Inside the rewriting system, because it's I mean it basically just captures the PTA, right?
Yeah.
So is it easier than generally speaking the rewriting theories and solving like
Well, it's,
reachability?
I don't think it's easier. I think it's two different paradigms that have their strengths, and yeah. And so the objective was to take advantage of those strengths. And as you say, the right theory are equipped with quite rich language, quite rich capabilities, whereas when we look at PTAs, it's a particular model that is really intended to model real-time systems. And so there are complementary things. So for example, this real-time dense time extension was something that was not trivial. But well, now that there are some things written, it's easier.
Yeah, I mean,
Yes,
I mean, you've visited my talk, right? So
Yeah.
You've seen the number of states, right?
Yeah.
So when I was seeing this, I was like, well, if we had a method to, I mean, we didn't write everything by hand, right? We had like ways to regenerate the automaton, but this might have been a nice method of writing the requirement, which might have been easier than what we did.
Yes.
So I was
That's
thinking
the
maybe
reason
there's
why
a
I
way-
asked you a question afterwards.
So maybe there is a way to translate it back
Yeah.
to the automaton
Yeah,
and then
yeah.
our analysis.
Yeah, I think that it is possible.
Okay, so for the interest of keeping on time, let's thank the speaker again.